welcome all. Today we are going to discuss Carnot cycle. It is an ideal cycle. It will produce maximum possible efficiency. Okay. So this Carnot cycle has four processes. One is process 1 to 2 is an isentropic compression. Process 2 to 3 isothermal heat addition. Process 3 to 4 isentropic expansion. Process 4 to 1 isothermal heat rejection. These are the four processes which are happening in Carnot cycle. Now I am going to draw the Carnot cycle PV diagram and TS diagram. Let us start with insulated cylinder. Fitted with a frictionless piston. Frictionless piston, and this cylinder is insulated. It is fitted with a frictionless piston. Okay, it is fitted with a frictionless piston. And this is the cylinder. Insulated cylinder. Frictionless piston. And so we will have here one insulator, non-plating material as an insulator, and we have here one source which is at temperature TH, and here we have one sink at a temperature TL. So temperature TH and temperature TL. Now we draw the PV diagram. This is the PV diagram. Isentropic compression takes place 1 to 2. Then isothermal heat addition, heat supply. The S is equal to constant, T is equal to constant. And then isentropic expansion, then isothermal heat rejection. So these are the four processes happening in the Carnot cycle. And we draw TS diagram also here. This is the TS diagram. This is the TS diagram. The TS diagram, the process 1 to 2 is isentropic compression, 2 to 3 is a constant temperature isothermal heat supplied, and isentropic expansion and isothermal heat rejection, right? S1 is equal to S2, S3 is equal to S4, and this is TH, and this is TL. This is TL. Okay. So we have drawn PV and TS diagram for the Carnot cycle. Assuming one kg of air is filled inside engine cylinder and the source at a temperature of TH is brought in contact with the cylinder head whenever the heat supply is required, and the sink at temperature TL is brought in contact with the cylinder head whenever the heat is to be rejected. I is a non-conducting material which acts as an insulator.
So,
Now heat supplied is equal to QSUP is equal to TH into S3 minus S2. This is for process 2 to 3. In a process 2 to 3. Then in process 4 to 1, heat rejected is equal to TL into S4 minus S1. In process 1 to 2, isentropic process, so Q1 to 2 is equal to 0 and S1 is equal to S2. Then process 3 to 4, isentropic process, Q3 to 4 is equal to 0 and S3 is equal to S2. Now, what is the efficiency of a Carnot cycle? Is equal to heat supply minus heat rejected by heat supply, which is nothing but W net by heat supply. Okay. So now I can say 1 minus heat rejected by heat supply. So what is heat rejected by heat supply? That is equal to 1 minus the TH heat rejected is TL into S4 minus S1, and heat supplied is TH into S3 minus S2. Since S1 is equal to S2 and S3 is equal to S4, I can write this as 1 minus TL into S3 minus S2 divided by TH into S3 minus S2. These two got cancelled, so I can write the efficiency of Carnot cycle is equal to 1 minus TL by TH. That is equal to TH minus TL by TH. That also we can write TH. So this this is the Carnot cycle efficiency. This is the Carnot cycle efficiency. By looking at this, now we can say the Carnot cycle efficiency is governed by only lower temperature of sink and temperature of source. If the temperature of sink decreases, efficiency increases. If temperature of sink becomes 0, then the efficiency of Carnot cycle is 100%. It is not possible. Similarly, the Carnot cycle is not at all practically possible. Why? Because here in isothermal heat addition to take place, we need to have very long heat exchanger, and not only that, the heat exchange process should take place at slow speed. Whereas the expansion process and compression process are isentropic processes which have to take place at very fast speed. So heat addition at constant temperature, heat rejection at constant temperature, both requires a very long heat exchanger and it has to take place very slowly. Whereas the isentropic processes should take place at faster rate. So in an engine, while designing an engine, it is not possible to design with one process at the higher speed and one process at slower speed. Hence, this Carnot cycle is not practically possible. And another one thing is, the efficiency of Carnot cycle can be increased. Carnot cycle efficiency can be increased by increasing the average temperature at which the heat is supplied, and by decreasing the average temperature at which the heat should be rejected. So hence we can improve the efficiency of Carnot cycle. Let us take one problem where Carnot engine works between temperature limits of 400 degrees Celsius and 40 degrees Celsius and develops (130 kilojoule work, network work. Determine thermal efficiency heat supplied and change in entropy during heat rejection. Now let us take with given data. The given data, so TH is equal to 400 plus 273, 673 Kelvin. TL 40 plus 273, 313 Kelvin, and W net is equal to 130 kilojoule. Okay, kilojoule. So solution. We need thermal efficiency. Is equal to 1 minus TL by TH. That is equal to 1 minus 313 by 673. So 313 divided by 673, that 1 minus answer is 0.5349, which means 53.49%. This is the first one. And second one is the heat supply. Okay. Heat supplied is equal to W net divided by the thermal efficiency. W net is 130 kilojoule divided by thermal efficiency is 0.5349. So 130 divided by 0.5349, you will get 243.04 kilojoule by kilogram. Then third one is the change in entropy. To identify the change in entropy, we need to find what is the heat rejection. So heat rejection is equal to, heat rejected is equal to heat supplied minus heat supplied minus W net. The heat supplied is 243.04 minus 130, so 113.04 kilojoule by kilogram. This is the heat rejected. Now we can write heat rejected is equal to TL into S4 minus S1. So we know what is heat rejected, 113.04. We know what is TL, 313, and the S4 minus S1 is the change in entropy during heat rejection is equal to S4 minus S1 is equal to 113.04 divided by 313 is equal to, so 113.04 divided by 313 is equal to 0.361 kilojoule by kilogram Kelvin. So next is a Otto cycle, a constant volume cycle. So why it is named as constant volume cycle means the heat addition takes place at a constant volume in this cycle, Otto cycle, which is used for mainly for gasoline engine. Used mainly for gasoline engine. Okay. Now it has four processes. The processes are 1 to 2. It is isentropic compression, and 2 to 3 constant volume heat addition, 3 to 4 isentropic expansion, 4 to 1 constant volume heat rejection. So all are reversible. So we can say reversible constant volume heat addition, reversible constant volume heat rejection. So these processes are drawn here in a PV and TS diagram. So I draw PV and TS diagram here. So this is the PV diagram. In a PV diagram, the first one is an isentropic compression. So isentropic compression takes place here, 1 to 2, S is equal to constant, and then the constant volume heat addition. So here the heat addition is taking place at a constant volume. So heat supplied, and this is the third stage. And 3 to 4 is expansion, isentropic expansion, and 4 to 1 is a constant volume heat rejection. This happens at constant volume. This is also happens at constant volume. Since heat addition takes place at constant volume, this process is also known as constant volume process. Then TS diagram. The TS diagram, The 1 to 2 is a isentropic compression process, and 2 to 3 is a constant volume heat addition. Constant volume heat addition. 3 to 4 is isentropic expansion, and 4 to 1 is a constant volume heat rejection. So this is heat supplied and this is heat rejected. So here if you say this is P1, P2, this is P3 and this is P4, and here this is T1, T2, this is T4 and this is T3. So I have drawn PV and TS. Now, what is heat supply? What is heat supply is equal to QSUP, that is equal to heat supply at constant volume process. So CV into, if this is happening at from 2 to 3, so T3 minus T2. This is the heat supplied. Then heat rejected is equal to, it is also happening at constant volume, 4 to 1. So CV T4 minus T1. So thermal efficiency is equal to W net by heat supply. That is equal to heat supply minus heat rejected divided by heat supply. So that is equal to 1 minus heat rejected minus heat supply. That is equal to 1 minus CV into T4 minus T1 divided by CV into T3 minus T2. This CV and CV got cancelled. So you get the thermal efficiency as thermal efficiency is equal to 1 minus T4 minus T1 by T3 minus T2. So this we can write like this: 1 minus T1 into T4 by T1 minus 1 divided by T2 into T3 by T2 minus 1. So let us take this as equation 1. Okay. Now take the process. Process 1 to 2, it is an isentropic compression. Isentropic compression process where T2 by T1 is equal to V1 by V2 power gamma minus 1, that is equal to R power gamma minus 1. I will take this as equation number 2. Then process 4 to 1 you can take. So 4 to 1 is an isentropic expansion. So here we can write T3 by T4 is equal to V4 by V3 power gamma minus 1. You can see here V4 by V3 is almost same compression ratio. It is nothing but V4 is equal to V1. We can say here V4 is equal to V1, V3 is equal to V2. So we can write it as V1 by V2 power gamma minus 1, that is equal to R power gamma minus 1 3. From 2 and 3 we can write T2 by T1 is equal to T3 by T4. So which gives, I can write like this, T4 by T1 is equal to T3 by T2. This I can apply this one as a fourth one. Substituting 4 in 1, I'll get, substituting 4 in 1, I'll get thermal efficiency is equal to 1 minus T1 by T2, that is equal to 1 minus 1 divided by T2 by T1. What is T2 by T1? T2 by T1 is equal to R power gamma minus 1. So from 2 I can write thermal efficiency is equal to 1 minus 1 divided by R power gamma minus 1. R power gamma minus 1. So this is the final expression for the efficiency, thermal efficiency by following Otto cycle. In this one, if you look at this equation, if compression ratio increases, thermal efficiency increases. It will go on increasing, but due to certain constraint, we have to maintain the compression ratio of 8 for an engine which operates under Otto cycle. Therefore, the compression ratio up to 8 is approved, and therefore the compression ratio increases up to 8, the thermal efficiency increases. Beyond that, we do not have engine with compression ratio more than 8. Now we will see one problem in Otto cycle. An internal combustion engine having compression ratio 5.5, so R is equal to V1 by V2 is equal to 5.5. What's an ideal Otto cycle? The pressure and temperature at the beginning of compression are 1 bar and 27 degrees Celsius. So 1 bar can be written as 100 kilopascal, and T1 is equal to 27 plus 273. Now it is 300 Kelvin. The peak pressure is given as 30 bar. So P3 is equal to 30 bar. Now we have to find, gamma is given as 1.4. We have to find pressure and temperature at all salient points, Astronomical efficiency, mean effective pressure, and we have to find all these things. To start with, let us draw the PV diagram to understand that. It will be easy for us. So PV diagram. Okay. PV diagram. So 1 to 2 is a compression process, and 2 to 3 it is a constant volume process. Then 3 to 4 1 to 2 is isentropic compression, 2 to 3 is a constant volume heat addition, 3 to 4 is isentropic expansion, 4 to 1 is a constant volume heat rejection. So, and this is clearance volume, and this is swept volume. Now we have to find out pressure and temperature at all salient points. Let's go with the first one. Pressure and temperature at all salient points. Process 1 to 2, we can write here the T2 by T1, it is an isentropic process. It is an isentropic process. So T2 by T1 is equal to V1 by V2 or gamma minus 1. So V1 by V2, you know it is 5.5. So 5.5 power 1.4 minus 1. So I will get minus 1. I want T2 for T2 is equal to T1 is 300 Kelvin. It is 5.4, 5 power 0.4 is equal to, so 5.5 power 0.4 into 300 is 593.29 Kelvin. Then P2 by P1 is equal to V1 by V2 power gamma, that is equal to 5.5 power 1.4. Therefore, P2 is equal to P1 as 1 bar and this 5.5 power 1.4 is equal to, so 5.5 power 1.4 is equal to 10.88 bar. Then process 2 to 3, it is a constant volume process which gives T3 is equal to T2 into P3 by T2. Therefore, T3 is equal to T2 is 593.29 into P3 is 30 and P2 is 10.88, that is equal to, so 30 divided by 10.88 into 593.29, you get 1635.91 Kelvin. Then we have to proceed to process 3 to 4. It is an isentropic process. It is an isentropic process. See here. T3 by T4 is equal to V4 by V3 power gamma minus 1. So V4 by V3 is R power gamma minus 1. Therefore, T4 is equal to T3 by R power gamma minus 1. So T3 is actually, we have found it as 1635.91 divided by the R value is 5.5 power 1.4 minus 1. So you get T4 as 1635.91 divided by 5.5 power 0.4. So 1635.91 divided by 5.5 power 0.4, 827.21 Kelvin. Then P3 by P4 is equal to V4 by V3 power gamma, that is equal to R power gamma. Now the P4 is equal to P3 by P4 by P3 R power gamma. P3 is 30 bar and this is 5.5 power 1.4. So I get 30 divided by 8.5 power 1.4 is equal to 2.758 bar. So now we found out pressure 1, temperature 1. Already it is given in the problem. P2, T2 we found out. T3 we found out, P3 is given in the problem. And we found out T4 and P4. So pressure and temperature at all salient points, we have found out. Then the second one is air standard efficiency. Air standard efficiency is equal to 1 minus 1 by R power gamma minus 1, that is equal to 1 minus 1 by 5.5 power 1.4 minus 1. Therefore, air standard efficiency is equal to 5.5 power 0.4, 1 divided by then 1 minus 49.43 percentage. That means 0.4943 is equal to 49.43 percentage. Then we have to find out mean effective pressure. Third one is the mean effective pressure. To find mean effective pressure, we need heat supply. So heat supply per kg of air is equal to heat supply is equal to CV into, whereas heat supply happens from 2 to 3. So CV into T3 minus T2. Okay. So CV is equal to 0.718 and temperature T3 is 1635.91 and T2 is 593.29. So I will get .6 kilojoule per kilogram. This is the heat supplied per kg of air, 714.6. Now we have to find out what is W net. So the net work done is equal to efficiency of Otto cycle into heat supply is equal to, what is the efficiency actually we get? 0.4943 into 748.6, you get 748.6 into 0.4943, we get 370.03 kilojoule by kilogram. Then we have to find out what is the volume of air taken inside, V1. So V1 is equal to RT1 by P1, that is equal to 0.287 into T1 as given as 300 Kelvin, and since here we are substituting kilojoule, we are substituting kilopascal here, 100. So you get 0.287 into 300 divided by 100, get 0.861 meter cube by kilogram. Now we have to arrive what is the mean effective pressure. Mean effective pressure is equal to net work produced divided by set volume, that is equal to W net divided by V1 minus V2, that is equal to W net divided by, you take V1 common term, you get 1 minus V2 by V1, that is equal to W net divided by V1 into 1 minus 1 by R. So what is W net? W net we got it here, which is 370.03. What is V1? You got it here 0.861. And 1 minus 1 by 5.5. Right? So you get the mean effective pressure as 1 divided by 5.5, 1 minus answer into 0.861, 370.03 divided by answer 525.27 kilopascal, that is equal to 5.25 bar. Okay. So with this we complete this problem. Whatever asked we have completed everything. We have found out all the answers.